Alright. Before I do the notes on ideal gas law, just a couple of comments. I actually mentioned it to the girls in the back there. One of the things that makes chemistry so tricky is that you have to do so many little steps. And if you mess up on any one of those little steps, the whole thing gets screwed up, right? Like, for example, I accidentally put down CO2 on the board there when it was supposed to be C3H8. I mean, an innocent mistake. I mean, it's not like I don't know what I'm doing. I feel like I'm pretty good at chemistry, but how easy is it to just write down the wrong chemical? They both start with C, right? Well, how does that screw it up? Well, then I used the wrong molar mass, right? And then you're going to get the question wrong. Does that make sense? You can do so many little things wrong in chemistry. So I said this to you guys before. If you want to improve your grades, probably the best way you need to do that is stop doing dumb little mistakes. I don't mean to be insulting, but just like that's probably where you're losing a lot of marks. Is stuff that you know what to do, and you're just not executing it properly. Does that make sense? Like, for sure, there's going to be some questions where you look at the question, it goes over your head, and you're like, I didn't know what to do. But there's probably going to be a lot of mistakes where you're like, I can do that. So, okay. One of the things that I mentioned to a few of you guys as well before we left is that all of these questions we've been doing before, they really hinge on the premise that we're operating at 25 degrees Celsius or 0 degrees Celsius, and that we're operating at 101 kilopascals or 100 kilopascals, like either STP or SATP. But like say on the previous question with the barbecue, who barbecues something at 25 degrees Celsius? That makes sense? Like room temperature steak. Like that's not gonna happen, right? So, the ideal gas law then, this is our last topic, kind of helps solve this problem for us, where if we're not operating under those standard kind of conditions, we need a way to find that ratio of 22.4 or 24.8, finding a different number to go there. Okay. That barbecue question, by the way, I mean, I think it makes a lot of reasonable sense that the numbers I gave you were reasonable. I find it terrifying to think that there's like 16,000 liters of gas, carbon dioxide given off just by my one barbecue over the summer. That's a lot, isn't it? But the problem with that equation there is that we know that gases expand when they're heated. And so we were doing those calculations based on 25 degrees Celsius. But like, isn't that gas going to expand even more when it's at 400 Fahrenheit? So anyways, that's our goal today. So you guys probably have already noticed the notes are pretty short. There's not a lot I need to add other than we're going to do a couple of examples, and I want to show you what the ideal gas law is. Okay. Quick review. These are properties of ideal gases, but I'm not going to spend time on that. You guys should know this. Okay. Here's what scientists then have been able to conclude. Boyle's law was that pressure times volume was always equal to some sort of constant. Charles' law was that pressure and temperature are a constant. Actually, that's wrong. Charles' law is actually that volume over temperature is a constant. My bad. In a way, Avogadro managed to figure out that volume and moles had a bit of a relationship to it as well. And so somebody smart, I don't know who, because he didn't name the thing after himself like a good scientist is supposed to, but someone managed to figure out that we can combine all of these kind of rules together in one big equation. And this is the equation. PV over NT is equal to a constant. N is moles. Sorry, if you've ever seen that before, N is defined as moles. The reason we don't go with M for moles is that M has been saved to use for mass. So P is pressure, V is volume, N is moles, and T is temperature. And this is known as the ideal gas law. The reason I think why we call it the ideal gas law is that this law works for any gas that's ideal. When would a gas not be ideal? When would a gas be real? Yeah, if it's so frozen because its temperature is so incredibly cold. Or the other condition? So low temperature is one condition. Exceptionally high pressure, yeah. So basically you can use this equation as long as the temperature is not like, say, 3 Kelvin. Okay. Or you can use this equation as long as the pressure is not like, say, 1 billion kilopascals. I don't actually know what the number is, at which point it stops becoming ideal, but this law basically should work. Okay. Someone was very clever then and managed to figure out what that constant was. And we're actually going to do this in a lab next week. We're going to calculate the constant value. They substituted some known variables into the equation. You know how like STP? STP is 0 degrees Celsius and 101,325 kilopascals. So they plugged in the 101 kilopascals. They plugged in 273 Kelvin, which is 0 Celsius. And then you guys know how like STP, I just told you it was like 22.4 liters per mole? Well, then they put in 22.4 liters, and they literally put in the number 1 mole. And they calculated a constant. Write this down somewhere. We've discovered that there's a constant number that all gases seem to multiply and divide out to give here. It's 831. Next week on Monday, I think it is, we're going to do a lab, and we're going to try to determine whether this constant really is 831 or not. And I've actually had some groups before where they get like 812, and they're like super duper close actually, which is kind of cool to be that close in a high school lab. I've had some groups where they get like 11.5. Like 11.5 is kind of close, but you know, so. Most of the time, though, the ideal gas law gets written a little bit differently. Rather than writing it in this format here, where you've got PV over NT equals a constant, they times the NT up to the other side, just so that you don't have to work with a fraction, because people aren't usually as happy working with fractions. This is actually what I learned the ideal gas law when I was in high school, and my teacher called it PV equals NERT. And it stuck in my head because that's so, like, I don't know, memorable, I guess. So I try to teach students that this is called PV equals NERT. NRT, NERT. This is the ideal gas law. Take pressure and times by volume. That's going to be equivalent to moles times R, which is now always going to be that 8.31 number, and T, temperature. So this is our last formula. And truthfully, this formula is pretty straightforward. So that's why I've only got 3 examples. So. Any questions so far? Let's try some examples. Okay, student does an experiment. There's a 31.6 liters of gas. There's a pressure listed. There's a temperature listed. We want to try to figure out how many moles there are. So, newest formula, PV equals NERT. What do we know? Well, we know pressure. Pressure was 127.6 kilopascals. Do we know volume? Sure, it was given to us. It was 31.6 liters. And what does N stand for? Do we know how many moles there were? Okay, that's what we're looking for, so I'm going to leave that one blank. I'm waiting for someone to come in the classroom or not. Makes sense. Hi. Do you guys remember what R was from just the slide like 2 slides ago? Yeah, 831. But make sure you watch the units for R. R has very odd units. It actually has 4 units altogether. The units for R are L times kPa over mole times Kelvin. I'm going to show you why this is important in a second, but write out its units. L times kPa over mole times Kelvin. That's the unit of the constant. By the way, for any of you guys who did that constant on the lab, the Boyle's Law lab, make sure you put units afterwards. You should always have units for things. Last thing, what's our temperature? 77 degrees Celsius. So 273 plus 77 gives 350. that make sense so far? Basically, I'm just plugging numbers in the formula. How do I get n by itself? Yeah, you gotta divide both of these numbers though. So divide by 831 liter kPa's over mole kelvins. Also divide by 350. So then you're doing the same thing over here. Divide by 831 liter kPa's over mole kelvins and 350. That can go. Yeah.
Can we just write R instead of writing out L times K?
Well, actually, this is actually why I want to recommend you write out those units. This is going to help you visualize and see everything that cancels, I hope. You see how this kPa right here, I'm going to use a different color. See how this kPa can cancel with this kPa? Over here there's a liters. It can cancel with that liter right there. See how there's a Kelvin down here on the bottom of the fraction? But on the bottom of another bottom of the fraction, there's a Kelvin right here. That can cancel. What's the only thing that doesn't cancel? Moles, yeah. Which hopefully makes sense because our question is going to ask us for how many moles there is. So I'm kind of going to be a stickler here. Write out the units. I know it's a pain because it's, it's a lot, but I don't know. I would recommend that if you want to be good at something, being lazy is not the best way to get there. So I know it's going to take you an extra second, but I think it's worth the while because it'll help. It's just a good practice of unit canceling, especially if you're going to keep going in chemistry or physics, especially. If any of you guys want to take physics with me next year. So. Okay, one last thought. When you guys put this in your calculator, have I shown you guys how your calculators are dumb and they don't understand order of operations very well? You need to make sure you put like the top of the fraction, like 127.6 times 31.6. You have to put that in a bracket and then divide by the bottom of the fraction, also in a bracket. Otherwise, your calculator is going to think that you're asking it to do something different. How many sig digs should I round this to? 3 is correct, yeah. Why not 2 for 77? Yeah, technically we didn't use 77. We used 350, so 139. Does that make sense? Any issues on the first one? Okay, let's go to the second one. I'll try to go a little faster with the second one. It's really the third question. It's the challenging one. So, here's another question. It's very straightforward again. The formula we're going to use is PV equals inert. Let's plug in what we know. Pressure. Do we know pressure? Technically, no, we don't know pressure. So I'm going to leave P there. Do we know volume? Yep, I was given volume, 0.0193 milliliters. Do I know moles? Actually, no, I don't. But I have a way of doing that, though. See how there's 30 grams right here? I can convert grams to moles. So I'm just going to do a brief aside here. 30.00 grams multiplied by a mole over a gram. Where do I find a way to do that? Molar mass. Well, molar mass of what? Neon. Neon, yeah. So find neon's molar mass. 20.18. So 30 divided by 2018. So I'm going to get a number here. I'm going to round it on paper, but don't round it when you use it in the calculator. I get like 1.4866 moles. Anybody else get that one as well? So I'm going to write 1.4866, but actually use as many decimal places as you can here. And just put dot, dot, dot there. Do you guys remember what R was? Yeah, it's always 831. And that is kilopascal liters over mole kelvins. And then we also have to times by our temperature. Sorry, I'm kind of running out of room here. 25 degrees Celsius is 298 Kelvin. Just going to put this aside. Does that make sense so far? So, how do I get pressure by itself then? Divide that out. So I'm just going to write this way down here. Pressure is going to be equal to 1.4866 moles multiplied by 831 kilopascal liter mole kelvins. And we're timesing by 298 Kelvin. And we get to divide all of this by that 0.0193 milliliters. Does anybody see my mistake yet? Good. I mean, I did this kind of on purpose just to hopefully illustrate a point, but you know how Michael asked me a second ago whether we could skip writing those units? This is the reason why I prefer you don't. This milliliters right here and that liter up there don't cancel. Does that make sense? So I know it takes an extra second to write it every single time, but my hope as a teacher is if I help drill into your minds that it's worthwhile to write that, maybe you'll catch that mistake. And you'll realize, hey, this moles and that moles cancels. This Kelvin and this Kelvin cancel. And then when you go around to canceling this liters, with that liters right there, you realize, wait, they don't fit. Does that make sense? So, how do I convert milliliters to liters? Yeah, I actually have to divide by 1,000. So this is already a very small amount of milliliters. It's going to become even smaller when we make it into regular old liters. So if I make that into liters, I've got to like move the decimal place over 3 more times. So like 1, 2, 3 more times. This is a very, very small amount of volume, I guess. Now the liters can cancel. And I think one of the other reasons why I really recommend write all those units in there is that the pressure is now in kilopascals. Because maybe the pressure would have been in atmospheres or millimeters of mercury. Right? But now we know for sure that the unit is kilopascals. So try to take that 1.4866. I have like a 20416 afterwards. Try to take that whole number times by 831. Times by, that's a 298, I think. And then divide by 0.0000193. Here's what I got. 1.91 times 10 to the 6, 7, 8 kilopascals. Anybody else get that? One more thought here. Not that our math is wrong at this point, but I do have one more point to make here. This is supposed to be the ideal gas law. Gases are not ideal under 2 conditions. One of the conditions is exceptionally low temperature, and the other one is exceptionally high pressure. This might be an example of exceptionally high pressure. 1.9 times 10 to the 8. I mean, that is like we're talking millions upon billions of kilopascals here. So this might be a question where I might have asked you, is this actually an ideal gas at this point? And you might have to argue, I don't think this is actually an ideal gas anymore. These molecules, if there's that much pressure, are probably so compacted, so tightly next to each other, that even though that they are molecules of what is ideally a gas, can they actually function as a gas? Well, no, they're so tightly compacted, they're probably acting like a solid. Does that make sense? Any questions? Sorry, to be quiet again. Okay. Okay, last one. This is really the question that I wanted to get to. The first 2 questions are very, how do I put it? If you know how to use a formula and you just don't screw up on the little details, the first 2 questions are fairly straightforward. This is a question where I want to do something similar to what we started class with. The only difference is that liters per mole value of 22.4 or 24.8. I want to change that around on this example. So We're going to decompose 36.2 grams of nitrogen dioxide. So nitrogen dioxide would be NO2. If you decompose it, what would that look like? What's it going to turn into? Yeah, N2 plus O2. And balancing it, you're going to want to put a 2 there and 2 there. Does that work so far? So the way you guys would have done this to start class, you would have said, okay, so I've got 36.2 grams of NO2. And one of the things you would have probably done is done a grams mole relationship, because that would cancel those guys out. We need a molar mass. Be very careful about whose molar mass you're talking about. We need NO2's molar mass, though. So 1 nitrogen, 2 oxygens, I get 4601. Another thing we're going to need at some point here then is we're going to need to try to convert this into volume. So we're going to need a liters per mole ratio. Here's the problem though. The only liters per mole ratios I've given you so far are either 22.4 or 24.8. And those are under very specific standard conditions. Is this under standard conditions? Okay, I'm going to leave that blank. We're going to come back to this in a second. That's kind of the whole point. I do want to kind of finish this question off though. This would be liters of nitrogen dioxide. It actually wants to know how many liters of total product you'd expect. I have a little clever trick for that. We no longer want to have NO2 because that's kind of what we want to get rid of. Really what I'm looking for is like how many total products there's going to be. And maybe here's a clever way of doing it. For every 2 NO2s, that's right here, how many molecules of products do you make? Well, you make 1 of these guys. You make 2 of these guys. Would it be logical then to say that you get 3 products? I mean, I'm not doing them on an individual basis anymore, but I'm just saying, well, collectively there's going to be 3 molecules for every 2 you start with. Does that make sense? It's kind of a fast way of not doing this twice. So, okay, here's what I'm lacking though. I need a number to go here. This is kind of the whole point behind this whole lesson is, what is this liters per mole number? Because I know it's not 22.4 and I know it's not 24.8. It's got to be something else. So here's where we use PV equals inert again then. So, write out PV equals inert, and we need to try to find a way to isolate this so that we get a liter on the top and a mole on the bottom. Which one of these variables here is going to be the liters variable? Volume. Okay. So I don't want the pressure next to the volume anymore, so I'm going to divide P to the other side. So now what I have is V equals nRT over P. Does that make sense? So that's volume. Volume is in liters. But I wanted it to be liters per mole. Which one of these variables is the one that's going to involve moles? Okay, so I'm going to bring N down to the bottom of the side over here. So what you're going to have now is a new equation that does this. Volume over N equals RT over P. Do we know what R is? 8.31, always. I think R will make more sense once we actually do a lab to calculate R, but at least for right now, if you can just accept I'm telling you what the number is, it's always this. Again, though, I really think there's value in just practicing writing down these units. It took me 4 seconds. Do we know the temperature? 260 Celsius. 533 Kelvin? That's what I got too. So I'm going to put 533 Kelvin right there. And on the bottom of this fraction, we're going to put the pressure. Well, it's 60 atmospheres. Can I just put 60 down on the bottom of this thing here? Hopefully, again, by me showing you units, you'll realize, well, this kilopascal can't cancel with an atmosphere. So I kind of have to do another little bit of a side work right here. 60 atmospheres multiplying by 101.325 kilopascals in 1 atmosphere. So you guys can see what I mean when I tell you that chemistry, there's so many little steps. Like just this one question here, how many steps have I done? Oh, like I got a conversion here and a formula here and an equation up here and a line of work here. Like there's kind of a little bit of work everywhere. That's one of the things that makes chem so challenging. I got 6079.5 kPas, by the way. Anybody else get that? Okay, so that's going down here. 6079.5 kPas. So let's cancel what I can. Here's a kPa canceling with a kPa. Here is a Kelvin canceling with a Kelvin. Anything else can cancel? What units are left then? Well, there's a liter left. And there's actually a mole left. This is kind of odd. Normally, I've always had just 1 unit left over. But here there's actually 2 units left over. So I'm going to leave them both. We take 831 times by 533, divide by that number. I got 0.72855, etc. Why was that useful? Yeah. You know how I have like a question mark sitting up here? Where I said I didn't know what my liters per mole value was going to be. Now I have my liters per mole value. So this 0.7258 number is what's going right there. That's kind of the whole point behind all of this lesson. I know it's a very roundabout way of getting there, but the ideal gas law is developed in part to help us try to figure out how to solve a question like we did earlier today when the temperature and pressure are not standard. Because, I mean, what are the odds the temperature is actually 25 degrees? What are the odds the pressure is exactly 100? So, now going back up to this line of work up here, take your 36.2, divide by 4601, times by that number if you can do it exactly, and times by 3/2. I got 0.85982, etc. Anybody else get what I got? Did you get something different though?
Yeah.
Okay, I'll come take a look with you in a second maybe. Oh wait, last thought, what are my units? Well, in this line of work way up here, the only thing that didn't cancel was liters. And what like species or like element or chemicals were we talking about? I guess products, yeah. Which I guess is what we were looking for. The question was, how much total products were we expecting? We'd expect that much total products. I do got to do sig digs though. So going back and doing sig digs, this had 3 sig digs, this had 3 sig digs. Technically this guy right here only has 2 sig digs. So 8-6 I guess. Okay. There's a lot on that one, eh? Let me just try to do a quick recap of all the skills you'd need to be able to solve a question like this. I mean, hopefully you guys can see how, to some degree, how I structure the way I teach. I try to teach you like a little piece at a time so that every day we can add something new to it. Hopefully you know how to write a balanced equation. Hopefully that's something that you previously learned. That was one skill you needed. Hopefully, as of yesterday, you were pretty comfortable working with a line of work where you have a whole bunch of stuff canceled. Hopefully that's something you're comfortable with. If not, I mean, we'll keep working on it, obviously. The thing we were lacking was the liters per mole number. So the new skill today is, can you take PV equals inert and can you rearrange it to give us a new equation here? And in this new equation, you need to plug in 3 numbers. 831 is always going to be one of the numbers. The other 2 numbers are going to be whatever temperature and pressure you're working at. Because, like I said, what are the odds you're working at 25 degrees Celsius? Who knows, right? When we do our lab on Monday and we're trying to calculate stuff, we actually want to measure the actual temperature and pressure in the room. So it might only be 22 degrees Celsius. That makes sense? So we should account for that. We can't just assume it's going to be close. Once you do all of that, you get a liters per mole number. And then that liters per mole number is the missing number that goes up here. Does that make sense? You guys can follow that? Okay. That's our unit. Basically, if I summarize it, there's a lot of properties I need you to know. You should be able to work with Boyle's law and Charles' law and the combined gas law. And then the most recent thing you should be able to do, you should be able to throw in grams and deal with masses as well. So mass might involve the ideal gas law, PV equals inert, or it could involve what we kind of did where you kind of start with the grams and do a bunch of canceling stuff too. Either of those could be a skill you have. So. Okay, I think I'm done.